Hi, this is Pat Hindle with mmWave Journal. Welcome to this online panel, Millimeter Wave Technology. So in this panel, we're going to discuss the latest design, test, and measurement developments in millimeter wave devices and systems. So just a quick rundown on the millimeter wave market. The global millimeter wave technology market size was valued at $3 billion in 2024. This is from Markets and Markets, and expected to grow to $7.6 billion by 2029 with a CAGR of 20%. So it's a pretty good growth rate. There were a lot of other market forecasts that were even higher, but I think they were probably very optimistic. So I took one that I thought was more conservative. And looking at the main market growth areas, so the US and Europe look like they're about going to double over that period of time, whereas Asia Pacific is going to triple, so more growth in that area, according to Markets and Markets. And a few of the drivers of this market that they listed were security and sensing, automotive radar, high-capacity 5G, 6G, and aerospace and defense. So we've seen millimeter wave scanners now replacing X-ray systems in airport security. And of course, automotive radar is certainly something that's expanding with more safety features and autonomy on the vehicle end. So we have a great lineup of panelists today, experts in all different areas. We have Pete Moosbrugger. He's Director of Advanced Antenna Technology at Corvo. Georgia Kelly, Product Manager at MathWorks. Gerhard Schoenthal, COO at Virginia Diodes, and Chris Markey, CEO of Markey Microwave. So welcome, everybody.
Thanks, Pat.
Thanks, Pat.
Thanks, Pat.
Thank you for having us.
Okay, so let's get started. So one thing I wanted to start with is just kind of overall, at millimeter wave frequencies, the link budgets and noise figures are really challenging. And so I want to ask, what are the most promising device and circuit innovations to improve efficiency and minimize losses are you seeing out there? Maybe, Chris, you could start as a device expert.
Well, thanks for having me, Pat. Everybody. So I think when it comes to specifically millimeter wave design and device, it's very unforgiving, I think, when it comes to the accuracy of your models. And you will spend much more time on the design process than you would at lower frequency. So in terms of innovations, I think there's been a lot of good work at Keysight with like network modeling for transistors. I think that there's a continuous improvement from the foundries in terms of PDK modeling. But in the end, I think companies like Markey, for example, are going to rely heavily on in-house IP development. Specifically, we almost never rely explicitly on a foundry vendor to design at these frequencies. And I think, unfortunately for the panel, I don't think that will be published as openly as maybe the community might want. But I would say that is certainly a unique feature of millimeter wave. Once you figure out how to device models and you understand your design flow intimately, you can unlock those frequencies, but it's much more difficult than at lower frequencies.
And Pete, how about you?
Yeah, I think, I tend to look at it as, the physics is the physics at millimeter wave. And so there's certainly a lot of challenges, but some of those challenges can actually turn into benefits. For example, it's certainly a lot of high attenuation at millimeter wave, but that in effect can kind of spin around and allow you to deploy more cell sites that are closer to each other because they may not interfere with each other. But I think one of the bigger advances over the last couple of decades has been silicon and the ability to develop silicon processes that operate at 45 gigahertz and above, and that's allowed deployments of things like SATCOM and 5G millimeter wave for both 5G and fixed wireless access using non-5G networks as well. And I think that in addition to the silicon advancement, I think GaAs and GaN have also marched higher and higher in frequencies, and so there's system level trades that need to happen there. For example, you can't dissipate the power in a phased array if you're transmitting 100 watts per element at millimeter wave without a lot of challenges, the way that you can at lower frequencies, just because of the physics of the phased array technology. So there's certainly, I'm seeing continued advancements across the board in all of the core semiconductor technologies, but also in the systems that they go in. And for example, printed circuit board based phased arrays are now commercialized at millimeter wave. And you see that with systems like Starlink, and with the systems coming online like Kuiper, as well as 5G networks as well. Okay.
Gerhard, anything you on your end?
Yeah, I'll just kind of piggyback on some of the stuff that Pete's saying. So, I think at the device level, if we're talking about millimeter wave going up into sub-terahertz and terahertz, that your PAs and LNAs are critical. And I think the advancements in silicon are great. Advancements in SiGe for consumer level type devices are great. But if you start talking about infrastructure, commercial type systems, defense type systems, I think the advancements that have been seen in indium phosphide and gallium nitride technology are important. At VDI, we've been working closely with Teledyne Scientific for many years to push the capabilities of the indium phosphide HBTs up to 250 gigahertz. And, programs like Starry Night and Algar are pushing the limits for gallium nitride and what it can do. And then on the LNA side, I think that there's lots of, particularly as you're going up to hundreds of gigahertz in frequency, there's good indium phosphide hemp technology coming out of organizations like Fraunhofer IAF and others.
Great. Georgia, did you have anything on your end?
Well, I'm from MathWorks, so we don't make devices or circuits, but we make software and models. And we see, in a way, the complementary aspects of, given that any component or any technology has its limitation, what else can you do to make it work better? So we see continuous use and interest of digital signal processing algorithm to compensate whenever possible such impairments. And in particularly talking about efficiency, we see continuous interest for linearization techniques of power amplifier and in general transmitters. And millimeter wave, it becomes very interesting because there is not almost all transmitters are phased array systems. So you open up the door to many, many possible different implementations for linearization options over the air, on board, with different ways of estimating, for example, the channel. And we see continuous interest in that, actually even more interest than in the past. And not only in the past, it used to be primarily for base stations, and now they're talking about linearization even in handheld devices and satellite communication systems. And I even seen the idea of applying linearization for receivers, blind linearization for receivers. That is indeed very interesting, very continuous application, essentially, of digital signal processing algorithms. And there is a lot more that can be said to that extent. Adaptive matching networks or automatic gain control with different techniques. I mean, there is a lot going on, essentially, from a digital signal processing perspective.
So speaking of simulation tools, the next question I have, Georgia, which I think you can kick off, is, so how good are today's simulation tools in predicting the real-world millimeter wave performance, particularly with non-idealities like packaging parasitics, mutual coupling, and thermal effects?
Yeah, it's. I feel at least that the tools have improved a lot, primarily in providing better ways to integrate and homogenize the results from different tools or obtained with different techniques. So as soon as we move into the millimeter wave range, no cable is just a cable, not line is just a line, no PCB is ideal. So integrating the results of measurements or the results of electromagnetic analysis is paramount. And I think that the tools have become a lot better with that. Not only integrating the results and simulating them efficiently is also very important, because the bandwidth of the signals is exploding. I've been doing simulations with signals that have signals bandwidth in the range of gigahertz, which means that the simulation bandwidth, if you apply a little bit of oversampling just to look at the nonlinearity, is multiple gigahertz. At that point in time, it becomes very, very challenging from a performance perspective. And to cope with that, simulation and modeling tools really have to become more flexible in allowing to raise and lower the abstraction level depending on the needs. What I always say is that there is a lot of physics, there are a lot of impairments, there are a lot of effects, but do they really matter? Do they have an impact at the end of the day? And estimating that impact is what matters. So that's very important, creating models that are realistic for the type of simulation that you want to perform. So for example, if you are, just to make a very simple example, if you are interested in designing a machine network, then the S parameters will be enough. If you're really looking into radar tracking scenarios where you're maybe monitoring and steering multiple beams at the same time and tracking systems, and you're interested in this robustness of your tracking algorithms, then probably you don't want to go down to the lower abstraction level of the S parameters, but we still want to take into account frequency dependency and dispersion in your models. So tools that allow you to trade off the fidelity and the speed are best, and that is where I think a lot of the innovation has happened, speeding up and abstracting away some of the physical effects.
Well, Chris, I know you've done a lot of work on your models and data to really transform all your designs into mimics. What do you have to say on this subject?
Yeah, it's a problem that we think about a lot, and I agree directionally with what George is saying, but I would say there's a couple issues I think at mmWave that are kind of unique or increasingly hard as frequency increases. First of all, the sim prediction is only really as good as your fab accuracy, and so we can, nothing's changed in 15 years in the EDA tools, I would say, to make mmWave easier or harder necessarily to simulate. Maybe they've gotten faster. But the problem is, and to George's point, I totally agree that the level of abstraction you use is the critical, I guess, designer intuition trade-off. Like, only experts really understand where they can trade the accuracy for the speed. The problem is at mmWave, you can't really trade as much. Like, for example, if I design an amplifier down at 4 gigahertz, the package basically doesn't matter. I mean, as a hand waving argument, at 40 gigahertz, the package is everything. So it's like, you go from maybe being able to get away with a 2.5D momentum simulation or something like that for your final tape out, to including the entire package, including the bond wires or whatever interposer you have, including the launch into the PCB. And then you hope that the PCB that was made for you is actually made properly, which is not, in my experience, always the case. To this day, at least US PCB manufacturing is still behind, I would say, compared to the rest of the world in terms of the reliability and accuracy of those boards. And so it's very common for Markey to get back essentially a perfectly fabricated mimic and a perfectly packaged mimic, only to discover that everything else messed it up in the measurement. So I guess my point is, I agree with George. The problem is there's fewer things you can trade for speed. because you're going to have to incorporate as much as possible if you really want it to have first pass design success.
Pete, how about you?
Yeah, I agree with everything that's been said. Most of my experience is either at the printed circuit board or array level, or the packaging level rather than the device level. But I'd reiterate that the key that still applies today is that you have to understand which of the parameters you need to model very precisely and control very precisely, and which ones don't matter, because the ones that don't matter will really bog down your simulation time and won't really add a huge benefit. And so that's where the art still comes in today of the designers, is understanding those trade-offs. But there are primary, secondary, and tertiary modeling features that you have to account for. Is really which ones do you select. But we're getting first pass designs at mmWave up at 37 to 40 gigahertz, where we're getting circuit boards out with a reasonably well understood distribution of manufacturing tolerances. And when you take into account those manufacturing tolerances and some of those corner cases, you can get arrays that work first time and then transition into production with thousands of units that are very consistent and very high yield.
Great. So speaking of packaging, we discussed a lot about that. So with the packaging becoming more difficult with the parasitics and increased sensitivity to dimensional tolerances, what advancements are you seeing in the area of surface mount packaging, antenna and package, chip scale packaging? What are you seeing there? Gerhard, did you have any inputs?
Yeah, and so I'll step back for a minute and start with tester measurement applications, which we're most familiar with. And, particularly as you go higher in frequency above 100 gigahertz, the chip and wire and metal integrated millimeter wave assemblies continues to work quite well. That technology is certainly for high mix, low volume type applications. As Pete was kind of alluding to earlier, at least for FR2 type situations from 26 gigahertz and at least to 40 gigahertz, maybe a little above, the SMT packaging, antenna and package, the chip scale packaging has been working quite well, as it's been going into iPhone Pros and similar type devices for over 5 years, with tens of millions to maybe over 100 million devices in circulation. I think as you get to 100 gigahertz and higher, this type of integrated packaging becomes more challenging, at least at the commercial and infrastructure type level. You'll still see a lot of metal housing and chip and wire type architecture, and I'm talking about like backhaul type instances, both terrestrial and non-terrestrial. But as the volumes increase and the price points become more sensitive, the manufacturers are going to be forced to work on 3D heterogeneous integration type packages. At those high frequencies, I think you'll maybe even continue to see bare die flipped onto those 3D heterogeneous integrated type packages. And that's generally where I see things going at the higher frequencies.
Chris, I know you've done a lot of work on packaging, and you said packaging is everything at high frequency. What have you seen, especially on your chip scale packaging?
Yeah, so we've basically converted virtually every product we have to our chip scale packaging, which is basically an overmolded lead frame using hot via technology. It works fantastically well. The main benefit is not even necessarily the electrical performance, it's the physical size reduction. So, a package that used to be 3 millimeters becomes 1.5 millimeters. And so it's great technology. I think the challenge is, it's one thing for Markey to be a component vendor, and we can put an attenuator in there or a mixer or an amplifier, whatever. It doesn't really matter. The challenge, I think, has more to do with what is the system level designer going to do with that component. And how are they going to deal with the interconnections? So is it going to be a surface mount? Is it going to be kind of heterogeneously integrated multi-chip assembly? Are they going to have a mixture of wire bonding and flip chipping? And then what's that interposer going to look like? I think those are the problems that we're seeing with our customers, because our customers are the ones building the systems. We're really just the component vendor, I suppose. And what I guess as a global corporate strategy now, we're headed towards this position where we believe that, especially at mmWave, Markey's going to have to develop all of the IP in that signal chain, such that we can give the customers the option to essentially tailor that signal path in a bespoke manner with ICs that work well with each other. Because it's not, as you go up in frequency, it won't be sufficient just to take like a random Markey part and a random mini circuits part and a random ADI part and put it on a board, and it's going to just work out of the box at 50 gig. That won't happen. And maybe it will work sort of, but it will be much larger than you want. And one of the huge benefits of mmWave is things can get small, especially with phase arrays. So all of a sudden now you're kind of left with this problem of how do you achieve the form factor and the integration level in an economic way. And that takes me, actually, Gerhard said something that triggered my thought, which is something that I think a lot of people probably take for granted with the test and measurement aspect of mmWave is how do you test a package, especially if it's like a surface mount package, up through 50 or 60 gigahertz. That's highly non-trivial. Like the actual like art of the test fixture, how the robotics are going to be, do fine pitch alignment and all that. It's a real art. I mean, we've spent years developing the ability to produce at scale mmWave surface mount products.
So maybe just tag on to a few things that Chris was saying there. I think in general with highly integrated packages, whether it's 3D HI or others, you get this question of known good die and known good packages, and you quickly get into the tyranny of numbers if you've got like yield issues, right? If you're known good, if you've got 90% yield on the die that are going in, and then that complicates the package, and you get really big yield fallouts. And so that's a big question on this advanced packaging, is the known good die and known good package question.
Yeah, just to respond, Gerhard, that's why we're trying to develop as much of the IP as we can, because at least we don't have the margin stacking issue. So if it was all of our own chips, if we have a couple skunky units, we can just throw them away. But if you're the end customer and you're buying multiple chips from multiple vendors, that margin stack means that you cannot lose yield, or else you're going to lose your margin, right? So it's a tremendously difficult problem, because known good die at these frequencies in itself is hard to, it's an expensive endeavor.
Pete, do you have anything on this? Do we see people having to sell more system on chip when you get to this level, or?
Well, I agree. Looking at the whole signal chain is really important. I think one of my experiences at mmWave, which is now Qorvo, is at least for the 5G and the SATCOM products, and even some of the DoD products that we develop for some of our customers there. They always had a heritage of high frequency testing. So they're doing high volume, millions of volumes of parts being tested at, the N257, N258 bands that are 24 to 30 gigahertz, and then, 37 to 43 gigahertz. And there's certainly more challenges there, but I think they had that expertise developed for the kind of packages that they were using that allowed that. I think one of the exciting things about the packaging that I'm seeing is that this was mentioned before, the 3D packaging, and I think in particular the enabling of mixture of silicon type technology and gas or GaN at millimeter wave. And so you can take the best of both worlds. Silicon, you have high density circuitry on there that you can do a lot of self-calibration. And now you look at extending that to some of the features with gas and GaN and compensating for some of the gas and GaN, either over temperature in performance systems or control of the gas and GaN itself. So those are absolutely feasible today. And then those can all of those technologies can be packaged together in a multi-chip module that's at commercial class cost points. So I think that's advancing pretty quickly, and I think is an exciting part of what we're seeing at Qorvo.
Okay, I wanted to move on to back into the modeling and simulation. Have there been any advancements in the workflows that are reducing development cycle times for millimeter wave devices and systems? I think, Georgia, you would be the expert here.
Thanks, Pat. Yeah, I mean, I think that lots of advancement, better simulation tools, faster simulation tools, but also new techniques. I mentioned before the integration of electromagnetics with system-level simulation, and the RF simulation is one of the techniques that really allows us to develop better systems. That also extends to the integration of measurements. So having the ability to toggle in between measurements or electromagnetic analysis results at the system level allows you to understand what are your margins and where you can innovate in terms of algorithms. One of the interesting things, for example, that we are seeing right now is the use of AI, artificial intelligence, in the space of primarily modeling and optimization. So, for example, just one of the cool things that we are doing, I think one of the cool things that I think is cool is that you need to integrate antennas with active front ends. Antennas, you need an anechoic chamber characterization, of electromagnetic analysis characterization. What we see is the use of AI to speed up the characterization or the modeling of the antennas so that you can integrate them with the rest of the system earlier rather than later. So, for example, it can be complicated to put an antenna and the phase arrays and in an anechoic chamber and characterize it completely for calibration purposes. But, well, maybe AI can help you in speeding up this process, or characterizing the antennas once they get installed on large structures where maybe manipulators don't have all the degrees of freedoms to move around the object. Well, AI can help again in reconstructing the pattern starting from sparse measurements, for example. And what I think is really helpful and important is the ability to toggle in between models, electromagnetic analysis, and measurements, and use the simulation as an integration platform before you actually build and prototype your system. Because effectively, once you build it and you prototype, everything is so well integrated, the probing in between becomes really hard to understand what happens. So simulation is a tool that can really help in figuring out.
So you mentioned measurement. So that was kind of another topic, was over the air, is kind of OTA measurement is important at millimeter wave, with the limitations of OTA characterization methods, where do you see innovation happening to overcome them? Maybe you and Gerhard can comment on that.
Yeah, very briefly. I see the usage of OTA in different ways, or very expensive. An anechoic chamber, even though there is a lot of innovation with portable chambers nowadays, are really, really, really cool. But the integration of analytical methods or even AI to speed up the characterization of the antennas, that's one area that definitely I see lots of innovation. And the other area of innovation is the use of relatively low-cost platforms for testing algorithms, rapid prototyping type of environments. So software-defined radios that allow you to experiment with new algorithms. They are completely different, both over the air, both have pros and cons, and both tied really well with the usage of modeling and simulation tools.
Yeah, so I'd agree with Georgia. We're certainly seeing more players in the OTA space. I mean, it used to be that you'd had NSI and MI, now NSI MI under Amatec or MGV, ETS Lundgren, and others like that. But over the past several years, you've had big players like Keysight and Rohde & Schwarz get in the compact antenna test range space. You've got new players like this Dutch company Antennex getting into the space, and then you've got novel type platforms like Millibox. A big part of this whole thing, especially as you maybe get to frequencies above 40 gigahertz, above what a 2.4 millimeter cable can do, is getting the signal to the device under test in a chamber of some sort. The loss in the cables above 2.4 millimeter cables just makes using cables above that kind of prohibitive. And so, that's what we've leveraged for a long time, is trying to bring with frequency extenders the signal to the DUT in the compact antenna test range, regardless of who the vendor is, so that you can perform that characterization, whether it's a large signal, small signal, or modulated signal type measurements. And I think that that's particularly important, getting that probe, getting that frequency extender, regardless of whether it's ours or someone else's, as close to the DUT as possible in the antenna test range.
Anybody else have comments on that?
I guess I have a general question kind of for Georgia and Gerhard, which is sort of like, Georgia touched upon this idea. She didn't say it explicitly, but the idea of like the digital twin came to mind. This idea that you kind of simulate the entire system first in a simulation domain or in a theoretical domain, and then you go and build it. And I guess it's kind of a question to both of you, which is like, have you seen at mmWave specifically, I guess, have you seen that become more of a thing, or are we still kind of in the land of prototype and iterate and prototype and iterate? Because like, especially like with VDI equipment, right? Like, do you guys simulate the entire thing, or is it more of a empirical build and improve over time methodology? And then I guess then the question I have for like Georgia is like you mentioned like orchestration or cross-platform simulation. MATLAB has a critical piece of the puzzle, but there's like other companies out there. Like my experience is that it's very difficult to have workflows between these tools. I don't know if you have any thoughts on like whether EDA has hopes of improving there to allow for using the best tool for the best functionality, I guess.
Great set of questions. I gotta go first, if you don't mind. Frankly said, I think in the past 2 years, the only work that I've been doing is helping customers in building digital twins for beamformers. So it's a constant, I can say, stream of requests, because the systems are getting very complicated. They have a lot of knobs. They have a lot of tunable parameters, and the people that ultimately build a radar or build a communication system, they need to understand how the different parts work. And the modeling simulation is the best way to help this type of understanding. What are the margins? And models have become incredibly, I would say, sophisticated for example, in modeling even statistical variations over frequency, over temperature. It has become a large data problem. And if you like, models have become, or simulation tools have been good in encompassing this type of diverse data to create models that are more specific for a given task. And I think that people have warmed up also to the usage of models in the sense that in the past I was had a lot of pushback that the models were not as accurate as the measurements. But we know that measurements are also not perfect nowadays, especially at millimeter wave. So people have become a little bit more, how can I say, relaxed with the fact that no matter what, there are uncertainties. But whether it is a measurement or whether it is a model, but maybe a model is good enough to understand and to develop algorithms and to see if the impairments match or not. So recently, I was with a customer who put together a fairly sophisticated pipeline, a chain of, I think it was like 45 or 50 components. I stitched them together to build a beamformer. It was for satellite applications, and then put it together in the lab, prototyped it, and it turned out that it was half a dB away from what the simulation predicted, which ain't bad, I would say, in terms of power levels. I would say almost too good for words from my perspective, in the sense that maybe there were margins to speed up or to simplify a little bit the models, but let be it. So yes, a lot of requests for models, and I think that from a vendor perspective of software provider, I think we have become a little bit better in helping the users integrating different tools. For example, one of the classical things that you can do is you get S parameters. Well, you can get S parameters from ANSYS HFSS, or you can get S parameters from CST, or from ADS. And you can put them in MATLAB and integrate them with the system level. That has been a long time. But for example, we have also become better in integrating entire data sets for phased array systems. What does it mean? Not only the S parameters, but also the embedded element pattern in the near field for multiple polarizations. So that in that way, we can really toggle in between the analytical models for the antennas versus more sophisticated electromagnetic analysis, and the same tools also work for measurements. So you can use exactly the same approach. And if you have sparse data, you can reconstruct with AI. So you have this plethora of tools that in a way, they all contribute and coordinate for the integration of different sources. So this is definitely a trend. You might argue it's not rocket science, but rocket science is often put together by smaller Lego bricks that, as long as they work together, they can build a nicer reality or a nicer experience, if I can say. I'm not sure if I answered your question. I mean, I was a little bit long-winded, but hopefully I covered some of your points.
No, that was
And I'll just add on quickly, Chris. I think as you go up in frequency, we continue to see our customers do quite a bit of build and iterate.
Do you think that will change?
I think always the simulation tools evolve and get better and better. I've got to guess at particularly the FR2 frequencies that they've got to be pretty spot on today, but above 300 gigahertz going to a terahertz, I think there's still quite a bit of build and iteration.
It's 300. When I asked the original question, I wasn't thinking 300, but is there like a limit, like in your mind? Is there like a limit where you start to build more versus simulate everything first?
I don't know. It's not my area.
Can I share an experience that we've had over the last couple of years? And it kind of ties together a number of questions. And this may be fairly unique to silicon because, I think that silicon has the ability to put in a lot of features that you can remove some of the manufacturing variations out of it, right? But we did a design with a customer of ours that was, we did the array part, we did the silicon ICs, and they did the rest of the system. And initially, this was a very high performance system with very low EVM in a 37 to 40 gigahertz band. And we designed the antenna to account for all the manufacturing variations. The devices themselves were in the mid 90% yield coming off of the IC at these frequencies. We did a lot of initial testing at the system level, and the whole system was designed together. So it speaks to the need to really look at this from a system level. That customer went through early testing that was extensive on some of the arrays that they were fielding. They were combining it with the rest of their radio. What they found and where they're at today is the only testing that they are doing is a final system level test that says, are they meeting a key metric? And they've got a test facility set up that's a very simple test, very fast test to do over-the-air testing to measure a key throughput metric, and it's a pass or fail test. They're getting 98% yield at the radio level, which is the only RF testing that they do in the system. So it's possible to get there. It's just you have to understand the technology that goes into it, and it has to be designed that way from the start to that's the way you're going to build it and test it.
Great. I just want to remind our audience, if you'd like to ask a question, enter it in the Q&A box, and we'll be happy to take some audience questions. But to continue our discussion, I wanted to move on to system architecture, because we talked about here how you have to look at the system level. What system architectures, phased arrays, hybrid beamforming, distributed MIMO, the different trade-offs you have, what is the most promising for next generation applications such as 6G and satellite communications? And I think, Pete, you're probably the most qualified here.
I think from my perspective, I think that the key part is really understanding what system you're trying to do. I think some of the additional comment I'd make is that you have to account for how are you going to test this at the end of the day? And my comments just spoke to that, right? It really needs to be designed in from the beginning. And all of these systems, and I'll take satellite communications at 30 gigahertz, for example. Depending on the system that you're designing for, some of these systems have extremely tight polarization control and irradiation. They require individual unit testing and validation at those frequencies. And so you have to be able to prove that at a qualification level, and then you have to be able to prove that in production you're meeting those kind of requirements. And so looking at it from a holistic perspective, test cost is a major factor in the delivery of a system. You can have the most exquisite technology in there, but if your test cost goes through the roof, then you don't meet your cost points, and the markets simply don't exist at the high cost points that were in the past. So you have to, we found that we have to really design the IC level to account for calibration of what you can push into the ICs. You have to account for thermal and the thermal management of the system. You have to account for all the manufacturing variations that go into the individual systems. And then you have to come up with a strategy on how you're going to test it. And I know that there were comments made about some of the emerging test companies that are out there. And I'll just throw out, like Antennax is a great example of somebody coming onto the market that I think is going to find a great niche for low volume or for low cost, high volume testing that covers a couple different areas at once. So all of those strategies have to play together from the system architecture all the way through the manufacturing, the validation, the qualification, and then into production to make sure that you meet that. Great examples of these are the Starlink system and what's going to come online with Kuiper. These systems, you cannot build millions or tens of millions of these arrays and be spending an hour a piece on them, testing them and tuning them and qualifying them. So their design strategies have been, we need to take that into account early, and everything needs to roll together into the cost models. And now you're seeing very exquisite arrays that used to be $100,000 a piece, best case, less than a decade ago, are now hundreds of dollars. So those are great examples of things that have emerged, and I think that capability is pushing higher and higher in frequency as we march on in time, which is just a natural evolution of the technology.
Actually, we have an audience question. What's the one thing you wish that test and measurement companies took into account better? What's lacking, that's not currently possible today? Anybody for that one?
Well, I definitely want to know what the others' opinions are so we can incorporate it.
Extremely cheap. Actually, I mean, not to be funny about it, but like literally the number one problem, especially startups face when getting into hardware in this field, is that the lab is equally expensive as getting your first prototypes, and it's a huge headwind if you want to, let's say, get into developing chips or something like that. Is how are you going to go measure it? And at these frequencies, forget about it. I mean, everything is very expensive, and I would say the economics of it are as problematic as the actual performance issues.
So do you feel that Millibox or Antennex, those type of solutions are partially addressing that, or are they still too expensive?
I don't know their price points.
I think they're starting to address that. I also think one of the strategy my team has taken is to get direct access to some of the test equipment. So, for example, we write our own Python code to control the antenna positioners, and it gives us a lot of flexibility with what we can do. And then we can scale that code across a lot of different platforms, like an EVM test stand or a temperature test stand, and we can very rapidly go in and modify that code to do unique things and unique test cases. So I think part of the balance is saying, what does my test need to perform to? So for a lot of these tests, a 25 dB down reflection off of surroundings is completely unacceptable. You can't do that if you're trying to measure low side lobe nulls, for example. But if you're doing EVM measurements, it might be just fine, because a 25 dB down reflection is not going to cause that much distortion in a complex signal waveform coming in from a side lobe. So it really depends on, I think, understanding what you're trying to test and then tailoring what you're trying to test. And then again, looking at it at the long range of what do you really need this test to do? Is it a qualification test or is it a production test?
Yeah, so I mean, I'd hop on to a little bit of what Pete's saying. We certainly here at VDI, in order to test out our test equipment, leverage Python type tools to set up specific test processes and protocols. And then on the price question, I mean, there is a large spectrum, even at say frequencies below 100 gigahertz or around 100 gigahertz and below. I mean, there are some hundreds of thousands of dollars types, up to millions of dollars type systems, and then depending on whether you're doing network analysis or just simple spectrum analysis, those price points can come down. And so I think it's expensive. I agree with Chris, it's expensive, but all test equipment to some degree is expensive. It's not consumer equipment. It is in fact test and measurement equipment, and not consumer or commercial type of equipment. But I think that there is a spectrum that we're addressing, and that our competitors and others are addressing in price, that is.
And let me respond to you, Gerhard, because I don't want you to think that I'm suggesting that your stuff is not fairly priced. It's definitely
I wasn't taking that
for what it does. I think maybe the bigger point, which is just the universal problem of millimeter wave, is that the markets aren't as large. So when you say commercial, you basically are saying, well, yes, at scale things get cheaper. That's like just the rules of economics. There aren't as many economies of scale that any of us can leverage at millimeter wave, except, okay, so maybe if you're dealing with like a satellite beamformer at standard 30 gigahertz bands, there's probably economy of scale there. But when you're talking about the long tail of applications and things like that, people can't recoup there's no ROI necessarily unless you increase the price. So that will be a perennial problem, at millimeter wave. People have been talking about 6G for a long time, and I think it sounds to me like it's been pretty overhyped. A couple of years ago at IMS, everybody was talking about D-band, and then nobody talked about D-band for like 2 years, and I don't even know if that's restarted.
Well, we still talk about D-band.
I know. Well, yeah. I'll put it this way: there was this.
Well, I think to address an issue with millimeter wave, I think in 5G that with millimeter wave, the industry maybe tried to run before it walked. And, I've been saying in these types of forums for quite some time now, if we're talking about 6G or some next G type communication, whether it's terrestrial, non-terrestrial, as you go up in frequency, as you get above 100 gigahertz in the sub-terahertz, we certainly need to crawl and then walk and then run. And I think you see that in things like backhaul, right? And so you look at the Ericsson microwave report for the past few years, E-band backhaul continues to accelerate. There's publicly available information. It's been in the trade press a lot recently about Viltronic and SpaceX and the huge E-band radios that they got contracts for. And so, that type of thing, that is crawling and then walking, and eventually that will make its way into the same shape that FR2 has made itself today. And so, I think that there's a progression there, and you will get some scale, and, you will see, like in FR2, things building on themselves.
I feel like FR2 was going to take off, but then FR3 got licensed, so everybody jumped to the lower frequency. If that hadn't happened, I think FR2 would have really accelerated.
Well, I mean, FR2 is maybe not as successful as some thought it would be. Again, try to walk before you run, but every NFL stadium in the United States has FR2 capabilities. It's every iPhone Pro and iPhone Pro Max for the past several years, and phones like that have N258, N260, and N261 on board. And so, the inertia is there for FR2, and there are countries like Japan where possibly these FR3 frequencies aren't going to be available, and they'll just need to stay at the FR2 frequencies. So I think that's still a question mark out there.
Good points. Okay, I think I want to wrap it up with one last question. Everybody can chime in. Looking for the next 5 years ahead, what is the single development, whether it's in device, system architecture, simulation, or measurement, will most significantly shape the millimeter wave ecosystem? I'll start in order here. Pete, why don't you go first?
Let's see. I think there's a couple areas if I can answer that, and I'll say that dovetailing back on the answer that was just given, I think there's a hype curve that comes out with these technologies as you go forward, and 5G is a good example of that. And there were a number of reasons why 5G didn't take off like it should have, including a lack of modem ecosystem, right? That's a thing that I could pinpoint. But I think fixed wireless access at millimeter wave closes a positive business case. So I think you'll see that to continue to deploy around the world. I think the satellite communication technology for phased array terminals will continue to explode over the next decade or so. And I think in the defense markets, networked communications, and all three are tied together. All three use phased arrays, and all three use a mix of technologies depending on the particular application.
Georgia, how about you?
So much to say. Definitely AI will play a role. creating models and simulation faster and quicker and absorbing more data. I'm not thinking fancy AI, I'm thinking really at AI as a tool to manage a large amount of data. We all have a large amount of data, large amount of measurements, and use this data more efficiently in a less manual error prone way. So I think that the AI will definitely come out as a tool, as an asset to develop better models and simulation. And then I think that a lot of I think also we will see a lot of convergence between sensing and communication. So systems that become more agile, more programmable, more software oriented, software driven. So tighter integration of digital signal processing algorithms, whether for correction, linearization, calibration, carrying better and more information. I think we will see a lot of that in the next 5 years. Very different things, but yeah.
Yeah, I'll come back to a couple of things that I mentioned earlier. I think that advances in semiconductor technology, whether it's SiGe, GaN, evolution of gas, indium phosphide, better semiconductor technologies to enable what we're currently doing at millimeter wave frequencies, FR2 kind of stuff, or going into true sub-terahertz and terahertz. And then the 3D HI, 3D heterogeneous integration, I think as you go up in frequency, that is going to become critical.
And Chris?
If you're talking about a single development, like the number one thing, I actually don't think it's technical in nature at all. I think it's going to be economics. I think it's going to be market demand for certain use cases that are desirable by human beings. So maybe the one that comes to mind is probably going to be millimeter wave satcom for like LEO and things like that. I think those are the kinds of things that can move mountains. Elon Musk is known for moving mountains, right? This is just, he could create the market for millimeter wave in a sense. And I think that it's pretty well understood that SpaceX and all those other guys are kind of moving towards higher frequency for higher bandwidth and all those wonderful things that we want so we can watch TikTok on our phone. I think that's more important than the technology. My assessment is that the technology is basically there or ready to be developed relatively easily if there are budgets to do so. To me, it's going to be an economic question mostly.
Great, a very pragmatic way to finish off. So I'd like to thank our panelists today, Pete, Georgia, Gerhard, and Chris, for a great session today. And thank Qorvo, MathWorks, and Virginia Diodes for being sponsors.